All right, it is time to begin. Oh, I should pass around the attendance sheet. Go, put your name on there. More limits. So I have a few things in mind. Obviously, if you have questions, you're always welcome to ask them. This looks really a little better. This is kind of like, it looks kind of funky, right? All this kind of jazz going on right here. Such as I don't know if there's anything I can do about that other than comment on it. It looks kind of funky. Yeah, I don't know why it's so like not great looking. Sorry about that. I wish I could. Let's see, if I make it brighter, is it better? Better? Not worse anyway? Okay, we'll go with that. If you ever need me to clarify something, I'm always happy to do so. Um, let's start with this. The limit as x approaches infinity of sine of x divided by x. And here's what I would say about limits with trig functions. If you are getting sine or cosine of something that essentially doesn't exist, whether it's something like this or it's something like the limit as x approaches 0 of x times, ooh, okay, what's going on there? Sine of 1 over x. Let me just make sure my connections are all feeling connected. Okay, everything? All right. What I am thinking about, like if you essentially have sine of infinity or cosine of infinity, which is not exactly the right way to say it, but close enough, we should be thinking about the sandwich theorem or the squeeze theorem almost always. So when I see something like this or something like this, I'm usually going to start by saying, well, I know something about sine or cosine. Sine of anything is always between -1 and 1. End of story. Well, not the end of this story, but like it's always true, right? The sine is always between -1 and 1. Whatever you're taking sine of, whether it's sine of x or sine of x squared or sine of e to the x or sine of something crazy, always between -1 and 1. So then if I'm trying to work with a limit like this, often what I'm going to try to do is I'm going to try to make the middle part of this compound inequality look like the thing I'm trying to take the limit of. So in this case, I'm going to divide everything by x. Now, technically, you have to worry about if x is positive or x is negative. So I don't really want to do all this, but technically, you can break this up into two cases where you say, okay, great. If x is positive, then we have -1 divided by x is less than or equal to sine of x divided by x is less than or equal to 1 over x. Because you divide everything by a positive number, you don't change the direction of the inequality. But if x is negative, you'd have to change the direction and say that -1 over x is bigger than or equal to sine of x over x is bigger than or equal to 1 over x. And what I would point out is that either way you write this, sine of x over x is still between 1 over x and -1 over x. So whether you're writing it this way or writing it this way, as long as these two outer things have the same limit, the squeeze theorem is going to apply whether we're thinking about it this way or this way. What I really want to say is you don't really need to worry about this so much. So let's look over here and say, well, if we take the limit as x goes to, oh, you know what else is true though? I'm taking the limit as x goes to infinity. So is x positive or negative? Definitely positive. So I don't actually need to consider this at all in this case. Now, if you were approaching 0, yeah, you would need to worry about it. Kind of. So here, I'm going to take the limit as x goes to infinity of each part. So I have the limit as x goes to infinity of -1 over x is less than or equal to the limit as x goes to infinity of sine of x over x. Is less than or equal to the limit as x goes to infinity of 1 over x. Okay, concept that's going to come up often. As x gets really, really, really big, what happens to 1 divided by x? Does it also get big? Or does it get small? It gets really small, really, really close to zero. So, and I should point out, when I say small, I mean close to zero. If I mean really super negative, I'll say negatively big. So something's like negative infinity, we won't say it's small, we'll say it's negatively big. So here, this is getting really, really close to zero. This limit is zero. Same deal over here. -1 divided by a really big number is also going to be really, really close to zero. It's going to be slightly, slightly negative, but very infinitesimally small and negative. And if something is bigger than or equal to zero and less than or equal to zero, you don't have any choice. It's got to be zero. So we can conclude by the squeeze theorem, the limit as x approaches infinity of sine of x divided by x is equal to 0. It is noteworthy, though, and I do think I should point out here, just as a note, it is true that the limit as x approaches infinity of 1 over x is, in fact, 0. As x gets really, really large, the reciprocal of x, or the inverse of x, gets really, really small. In fact, that's kind of one of the reasons we call it the inverse function, right? 1 over x is the inverse of x, because literally whatever x is doing, the inverse of x has the inverse kind of, the word I'm looking for is not coming to me, the inverse thing, right? If x is getting big, the inverse of x is doing kind of the inverse thing, and it's getting small. If x is getting small, 1 over x is going to get big. Okay, so let's look at a seemingly similar but altogether different limit. Let's look at the limit as x approaches 0 of sine of x divided by x. And here we could plug it in, right? It's not something where we can't just plug in infinity. So we plug in 0, we get sine of 0 divided by 0, which is 0 divided by 0, which is an indeterminate form. I just want to point out, 0 divided by 0 really could be anything, right? Like, if you have 0 divided by 0, I'm going to get 17. Does it work? I mean, it does. It works kind of in a stupid way, but 17 times 0 is what? 0. 0 minus 0 is? And my remainder is 0. That means the division worked, right? Kind of like, 12 divided by 3 is 4. 4 times 3 is 12. 12 minus 12 is 0. That's what we're looking for when you do division, is a remainder of 0. Now, this isn't the right answer here. But the point of what I'm doing is, right, this could have been anything. It could have been 17 or 217 or 2,170. And regardless, this division still works, meaning that when you have 0 divided by 0, it can be anything. So really, any result is possible. But again, as I was saying last time, what that really means is we have to do more work, because there's a specific value each limit's going to have if it exists. And how do I want to talk about this? So how much do we care about knowing how this works? I could just tell you what it is, but that seems kind of boring. I could tell you, and you would believe me if I said that the limit as x approaches 0 of sine of x divided by x is equal to 1. We could look at the graph. If I was quick here. That's not the button I meant to press. The graph. And if we graph sine of x divided by x, if we zoom in here, it certainly is getting, in fact, here's a better way to do this. Instead of zooming in, you could make a table. One could make a table, I could make a table, and start plugging in values of x like 0.9 and 0.99. Oops, so I'm trying to get close to 0, not close to 1. The output's going to be 1, 0.1 or 0.01 or 0.001. And the closer we get to 0, and see, sometimes you just get close enough that it estimates it to be 1. Or if you're on the other side as well, if you're plugging in negative 0.01, negative 0.001, we get really, really close to y values of 1. If you actually go look at the graph, though, like if you tried to click on the 1 there, sorry, I've kind of messed it up now. Let me delete this table. But if you actually try to delete this table, if you're trying to hover over that point there, it'll show that it's undefined at 0. So even though, right, if you look at this from the right-hand side, we're getting really close to y value of 1. From the left-hand side, we're getting really close to a y value of 1. At 0, the function's undefined, not surprisingly. But the limit still is 1. So we can see that graphically, this is true. I'm sorry. Sorry. You can see what I'm writing. That's right. That's right. So how much more should we say here? I think we should say a little bit more because it's kind of interesting. So I would say this next part I'm going to write down, you probably don't need to write down. You definitely don't need to be able to reproduce, but I do think it's kind of worthwhile. So let's take a minute and take a journey through seeing how this limit actually is equal to 1, because it's kind of an interesting geometric argument. So, and there's actually a couple ways of doing this. I was looking at one of your teacher's notes. He had something slightly different than what I've seen before. It's totally fine. So let's look at this for a second. Look at the circle of radius 1. I'm going to say that this is an angle of theta. I'm going to do a couple things. I'm going to label some points here. I'm going to label this the origin. We'll call this A. We'll call this B. We're going to drop a perpendicular from B down to that segment right there. And we're also going to then draw another little arc like this. So that whatever this point is here, let's call it C. This point here, let's call it D. This length OD and this length OC are the same length. So it's kind of like you have a little slice of pie of a circle. So both this little slice here, OCD, and this larger slice here, OAB, are both kind of slices of pie of either a bigger pie or a smaller pie. Okay. Couple of observations here. Observation 1, this slice of pie, OCD, I'm going to draw a little pie slice here. The slice of pie, OCD, has less area than the triangle, OCB. And that triangle has less area than the larger slice of pie, OAB. Good so far? Good so far. Okay. Does anyone remember the formula for the area of a sector of a circle? And the answer I'm expecting is no. I don't expect that anyone actually remembers the area of a sector of a circle. If you do, that's great. Here's what it is. Oh, actually, let me show you how I would think about it. So I do imagine many of you know the area of a circle formula. Like if I had a circle, good old circle over here with a radius of r, the area of that circle would be pi times the radius squared. I'm going to write this in kind of a nonsensical way for a second here. I'm going to write this as 1/2 times 2 pi times r squared. And the reason I'm writing it that way is because if you go all the way around the circle, what's the angle? 360 degrees, or in radians, 2 pi radians. 2 pi radians. What if we did half a circle? I'm going to ask 2 questions for half a circle. First of all, what's the angle for half a circle? Pi radians. And the area should be half the area of a circle. So for half of a circle, it's going to be 1/2 times pi times r squared. Or in other words, 1/2 times the angle that is subtended, I hate that word, by the way, but it's the right word to use, times the radius squared. And that formula actually is generally true. This, if you have a circle and the angle is theta, then that area there is going to be 1/2 times the angle theta times the radius squared. Kind of neat. Okay, great. back to what we're doing over here. That means we can write the formula for the areas of these things. So this larger slice of pie, or sector is the more official word, this length OA and this length OB are both 1, right? It was a circle of radius 1. So we say, okay, great. We have 1/2 times my angle theta times my radius squared. Triangle is a little bit different. The area of a triangle is 1/2 base times height. That's going to be 1/2 times the base, which is OC, times the height, which is BC. And then for the smaller triangle, again, not smaller triangle, smaller slice of pie, smaller sector, the formula still holds. It's going to be 1/2 times the angle theta times this radius squared, which I'm just going to call it OC. Sure. Please ask questions if you have. Yes.
0 or 6 next to the A at the bottom.
Actually, it's a theta. Sorry. Other questions? I have a question. Where's my water? There it is. Okay. Couple other things here. So if I look at this triangle OCB for a minute, I'll draw it over here again. I'll point out that the hypotenuse of this triangle has a length of 1. So if I was going to find, say, sine of theta, it would be the opposite over the hypotenuse, which is just going to be the length of BC divided by 1, which is just the length of BC. Similarly, cosine of theta, which is the adjacent divided by the hypotenuse, is the length of OC divided by 1, which is just the length of OC. So great. I'm going to take this and replace each OC with cosine of theta and each BC with sine of theta. Yeah. And I guess I'm going to multiply everything by 2 as well, because I don't need those 1/2s. So I'm going to multiply everything by 2, and I'm going to say I have theta times OC gets replaced with cosine. So I have cosine squared theta less than or equal to OC is cosine theta, BC is sine theta. And here I'm just multiplying by 2 and getting theta. Happy to provide clarification about anything I've done. Okay. Okay, now I'm going to start thinking about what I'm trying to get to. This is all in the kind of quest to find or to show what a catch. The limit as theta approaches 0 of sine of theta over theta is equal to 1. I'm trying to use the squeeze theorem here. So I really, really like the middle part of my compound inequality to look like the thing I want to take the limit of. So I'm going to do 2 things. I'm going to get rid of that cosine. So I'm going to divide everything by cosine. So divide by cosine of theta, and you're going to get theta times cosine theta less than or equal to sine theta less than or equal to theta divided by cosine theta. And then lastly, we're going to divide everything by theta to get a sine theta over theta. So dividing by theta, I'm going to get just cosine theta less than or equal to sine theta over theta less than or equal to theta over cosine theta divided by theta means this theta here gets divided by theta and we get a 1 over cosine theta. Cool. I have the thing in the middle that I'm trying to take the limit of, which is almost always what you're trying to accomplish if you're trying to use the squeeze theorem. Is the middle part should look like the thing you want to take the limit of, but you can't take the limit of. Actually. So now we don't take the limit of that. We take the limit of the sides. I don't know, the things surrounding it. Got it cornered. So we take the limit as theta approaches 0 of cosine of theta. We can just plug in 0. And what's cosine of 0? It is indeed 1. Similarly, the limit as theta approaches 0 of 1 over cosine, also known as secant, is going to be 1 over cosine of 0, which is 1 divided by 1, which is 1. So since the right side limit is 1 and the left side limit is 1, we have no choice. The middle thing has to have a limit that is equal to 1. Cool. We proved it. Kind of neat. I'll also point out another geometric thing you can think about is that this length here, this BC length, really is the length of sine of theta. And this arc length here from C to D, nope, that's not true. This arc length here from A to B, that arc length really is the length of theta. So what we're saying is, as that angle gets smaller and smaller and smaller, this vertical length here and this arc length here essentially get closer and closer to being equal to each other. So when this angle is super duper small, that vertical length and that curvy length are essentially, the same. That's what this limit really says. Okay, so now, you need to know how to do this? Definitely not. No one's ever going to ask you to do this. But it's good to have seen it. Now when I say the limit of sine of theta over theta as theta approaches 0 is equal to 1, be like, yeah, I remember that. I believe that. That's true. Most of the time, I try to show you why things are true. Occasionally, I'll be like, no, we're just going to buy this. And like L'Hopital's rule later on, we might be, well, okay. But for now, we try to show things are true if they're true. So more generally, what I like to say is that if you take the limit of sine of some stuff over the exact same stuff, as long as that stuff is going to 0, that limit has to be 1. So here's an example you've already seen. The limit as x approaches 0, sorry, not 0, as x approaches infinity. Is that what I really want? Yeah, sure, fine. Of x times, this is not an example you've seen exactly, but fine. Of x times sine of 1 over x. Check this out. I'm going to rewrite this so it looks like that. So you might not think it looks like that because I have to have stuff going to 0 and sine of stuff over the same stuff. But I do have this here. If I rewrite this as the limit as x goes to infinity of sine of 1 over x, and instead of multiplying by x, we're going to divide by the reciprocal. Those expressions are the same, or I should say equivalent. Now let me ask you, do I have sine of some stuff over the exact same stuff? Yes or no? For sure, yes. Is the stuff getting closer and closer to 0? Also, yes, because as x goes to infinity, 1 over x gets closer and closer to 0. So this meets the criteria. This limit is definitely equal to 1. It's kind of cool. Later on, near the end of the quarter, we'll revisit this limit and talk about how you can use L'Hopital's rule to find it. But at this juncture, we don't have access to that particular concept or idea, even though you might have already heard of it. Let's see here. Not what I'm looking for. 1 second. So let's look at something a little bit more complicated. So what if we had the limit as x approaches 0 of sine of 5x over 2x? So close, yet so far. Certainly, I have sine of something that's going to 0 and a denominator that's going to 0, but they aren't the same. So what we're going to do is we're going to make it so they are the same. There's a couple different ways to do this. Here's what I think works the best. I'm going to rewrite this limit as x approaches 0. I'm going to write 2 fractions. One where sine is on top, sine of 5x. One where 2x is on the bottom. And now I'm going to ask myself, what do I wish I had beneath sine of 5x? I wish I had 5x there. Great. Wishes come true. But now that I've divided by 5x, I also need to multiply by 5x so that I'm not actually changing the value of anything. Let me change this real quick here. Welcome, Brian. Pin my picture here. this thing never wants to go away. There we go. Okay, cool. So now I'm going to use one of those limit laws that says the limit of a product is equal to the product of the limits. This is equal to, no, I'm not actually. Although I could, I'm gonna do something smarter. I'm gonna cancel those x's. Say it's equal to the limit as x approaches 0 of sine of 5x divided by 5x times 5 halves. And really at this point, you should just say it's equal to 1 times 5 over 2. Because the limit of sine of something over the same something, as long as that something is going to 0, the limit's equal to 1. But if you wanted to show more steps because your teacher asked you to, you could say, oh, limit law, this constant multiple gets to come out in front. And so you have 5 halves times the limit as x approaches 0 of sine of 5x over 5x. And then we know that this limit is equal to 1. So we get 5 halves times 1, which is equal to 5 over 2. So when I see a limit like this, where it's sine of something over maybe a slightly different something, I'm usually trying to make the denominator part, or the thing that's not in the sine function, the same as the thing that's in the sine function. So let's look at a couple more examples. I can move the pieces of paper around. So let's say we wanted to find the limit as x approaches 0 of sine of 6x squared over 2x squared. I happen to prefer doing it this way just because it's always worked for me, but you are welcome to do something else. Like in this case, if you wanted to, you could just multiply by 3 over 3 and see that the 3 on top would kind of stay out in front and the 3 on the bottom would make the bottom equal to 6x squared. That works fine when the things are nice multiples of each other. It works less fine when they're not. So again, if it were me, I would do this instead. I would say it's limit as x approaches 0, and I'd break up my fraction into 2 fractions. Sine of 6x squared over blank, and then blank over 2x squared. And then, just like last time, what do I wish I had beneath sine of 6x squared? I wish there was a 6x squared. But if I divide by 6x squared, I also have to multiply by 6x squared. And then we can cancel the x squareds over here. I don't think you need to show much more work than this. We know this limit's going to equal, well, this is sine of a thing over the same exact thing, and that thing is getting closer and closer to 0. So it's perfectly legitimate to say this is equal to 1 times 6 over 2, which is 3. It even works if things are flipped around. For example, if you have the limit as x approaches 0 of 2x over sine of 3x. Let's actually back that up for a second. So what if you have the limit as x approaches 0 of x over sine of x? So here I'm going to use one of those limit laws. I'm going to rewrite this in a way so that it looks like something I know. I don't know what the limit of x over sine of x is yet, but I do know the limit as x approaches 0 of sine x over x is 1. So I'm going to rewrite this as the limit as x approaches 0 of 1 over sine of x over x. Certainly valid, right? If you were to flip this and multiply by 1, you would end up back where we started. And now we're going to use 2 different limit laws. The first one being that the limit of a quotient, the limit of f of x over g of x, is equal to the limit of the top thing divided by the limit of the bottom thing. And then we'll use another limit rule or law. I don't know, limit law, limit rule, whatever you want to call it. That the limit of a constant is just that constant. So the limit as x approaches 0 of 1 is just 1. And the limit as x approaches 0 of sine x over x, we already know is equal to 1. So we get 1 divided by 1, which is 1. So it actually doesn't matter which way you write it. If it's x over sine x or sine x over x, as long as the stuff is the same, limit's going to be 1. So in this example here, we could totally rewrite this as the limit as x approaches 0 of 2x over blank times blank over sine of 3x. Now you have to be a little bit careful. You want to make sure you're always matching what's inside the sine function or what the argument of the sine function is. So I know that I want above my sine of 3x, I wish I had a 3x. And then I have to balance that out. So if I have a 3x there, I'm going to divide by a 3x over there to make sure that we get the same thing. As we've done so far, the x's cancel there, and you end up getting 2/3 factored out in front of the limit as x approaches 0 of 3x over sine of 3x. It's probably one more step than I actually need to take. And then we have 2/3 times this limit has to be 1 because you've got something over sine of something, and the somethings are both going to 0. You might start to notice a pattern in that if you have sine of something divided by the same or by something else, and it's essentially just multiple of x over multiple of x. In fact, instead of trying to say words, I could just write it out. Essentially, if you have the limit as x approaches 0 of sine of some multiple of x over some different multiple of x, it's pretty easy to see that we're just going to get a divided by b here. You still have to show the work, but you kind of know what you're going to get. It does get a little more complicated though. If you have different powers of sine. Whoops. I'm just going to see the things. For example, if we had the limit as x approaches 0 of sine cubed of 2x over 3x cubed. I'll tell you right off the bat, the answer is not going to be 2/3. So here's what I would do. I would do the same thing I've been doing this whole time. I'm going to write it out, but I don't want to write just sine cubed. I want to write sine times sine times sine. So I'm going to write sine of 2x divided by blank times sine of 2x divided by blank times sine of 2x divided by blank times blank divided by 3x cubed. That's what I would choose to do here. Beneath each sine of 2x, I wish I had a 2x. Great. If I put a 2x there, I got to put a 2x there. If I put a 2x there, I got to put one up here. 2x there, I got to put one up there. I'm just going to simplify this. So I'm going to rewrite this as the limit as x approaches 0 of sine of 2x over 2x times sine of 2x over 2x times sine of 2x over 2x times the x's cancel, right? X times x times x is x third divided by x third divides to 1, and 2 times 2 times 2 divided by 3. So you end up getting the limit of that's 1, the limit of that's 1, the limit of that's 1, and that is 8/3. You could write another step if you wanted to. I don't think you should have to write another step here, but if I was trying to use those limit rules, I might write this as 8/3 times the limit as x approaches 0 of sine of 2x over 2x times the limit as x approaches 0 of sine of 2x over 2x. Ugh, I already got this immediately. Times the limit as x approaches 0 of sine of 2x over 2x. And then each of those limits is equal to 1. Again, just using the limit law that the limit of a product is equal to the product of the limits, as long as they all exist. Right? There's a rule that says the limit of f times g is equal to the limit of f times the limit of g. That's essentially what we're using here. That's equal to 8/3 times 1 times 1 times 1. What if we use tangent instead? You might think, well, James, tangent is completely different than sine. We're not going to get anything close to the same thing. And I would have agreed with you when I first learned this too. And then I would say, oh, wait, no, it's not going to do that because here's what happens. We can think of tangent as sine divided by cosine. So we're going to write this as the limit as x approaches 0 of sine of 5x divided by cosine of 5x times 3x. It is appropriate and correct to write it that way. Right? Sine divided by cosine divided by 3x ends up simplifying down to sine divided by the product of cosine and 3x. And now we're going to break this apart into pieces that make sense. I want to write this as the limit as x approaches 0 of sine of 5x over blank, just like I did before, times blank over 3x, and then you got this cosine of 5x all by itself out here. Cosine of 5x isn't problematic. Because if we plug in 0, what's cosine of 0 going to be? 1. So that's going to be just fine. Whatever's going on over here, this is not going to affect it. So just like the other 3 times, 7 times we've done this, I wish I had a 5x beneath sine of 5x. If I have one there, I need one up there. And now let's just not write all the things. Let's say we're going to have, great. The limit of sine of 5x over 5x is 1. 5x divided by 3x simplifies to 5/3. And 1 over cosine of 0 is just going to be 1. So we end up with 1 times 5/3 times 1, which is 5/3. So it's kind of interesting that in this sort of limit scenario, sine and tangent actually kind of act the same way. Kind of neat. If you think back to the geometric interpretation I described a little while ago, the reason that works is because, so what I said before was that as we get closer and closer here, this length here and this length here become, sorry, you can't see that, apologies. That this length for sine and this length for the theta get closer and closer to each other. If you think about tangent, tangent is the opposite side divided by the adjacent side. So as we get like way down here, well, the opposite side is still the sine side, and the adjacent side is getting really, really close to 1. So it's like you have sine divided by 1. Oh, that's going to be close to the thing that it was close to before. So it's not really that different. Kind of neat. All right, is that enough of the trig stuff? Hopefully. Let's take a look at my notes here. Let's be sure. Is there anything else I'm forgetting about? No, I think we're good. Yeah. All right, let's go that direction. So, sorry about that. You don't let's recap a little bit. So we've talked about, mostly last time we talked about limits that were 0 over 0 types. So reminder, limits. What do we do? First thing we do is we plug in whatever x is approaching. And if you get a number, great, end of story, typically. But usually we don't. I should write that out though. And if you get a real number, stop. But usually what happens is we get a 0, 0. 0 divided by 0. And we talked about a few things we can do. Typically, if we can, we would like to factor and cancel. Or we can't do that. We might try multiplying by a conjugate if there's a square root conjugate I can spell. Or we might try getting a common denominator. Or we might try some other stuff, right? Like we might try some trigonometry tricky stuff. Trigonometry tricks. Like last time we talked about, we had a limit as x approaches pi over 2 of 1 minus sine x over cosine x, which was a 0 over 0. We multiply both the top and bottom by the conjugate. We multiply by 1 plus sine. And that was how we dealt with that. And we just saw for another 0 over 0 type for sine x over x, what to do with that. So it's not complete. We couldn't really make an exhaustive list, right? We're kind of making kind of guidelines as far as what to do in the face of certain limits. And now what we're going to explore is the cases where we get not 0 divided by 0. Fortunately, they're not too terrible. So let's look at some examples. One second. See my examples. Sorry, what's that? Sure. So what about the limit as x approaches 1 from the left-hand side of 2x plus 3 divided by x minus 1? Again, before I do anything else, I'm going to try plugging it in. If I plug it in, let's see, I plug in 1, I get 2 times 1 plus 3 over 1 minus 1, which is 5 divided by 0. And I will say this is undefined. Unfortunately, there's not a whole lot of work to do here. In fact, almost all the time, when you have a not 0 divided by 0, there isn't very much work to be done. You really just have to do a couple things. One of the things is to decide whether the denominator is slightly positive or slightly negative. I know I wrote 0, but really, we're not actually at 1. We're really, really close to 1. So what we should be thinking here is that limit as x approaches 1 from the left of 2x plus 3 over x minus 1. Yeah, we're going to get 5 on top, but on the bottom, what I should be thinking is, well, I'm plugging in a number just slightly left of 1, like x equal to 0.999. If I do 0.999 minus 1, are we very, very slightly positive or very, very slightly negative? We're very slightly negative. I like to write that as a 0 with a minus sign as a superscript.
Why are we finding that?
Well, so I'm just talking about the denominator right now. So I'm just saying that the denominator, if I pick a number that's a little bit smaller than 1, a number less than 1 minus 1 is going to be negative. So now we have a positive number divided by a negative number, and the positive divided by a negative is going to be negative. Negative what? Well, let's actually plug in 0.999 here and see what happens. I'm going to plug it to the bottom. The top I'm just going to pretend like it's 1 because it's annoying to plug in the top. So if I actually plugged in 0.999, I would have essentially 5 divided by 0.999 minus 1, which is 5 divided by 0.001, but it's negative. And 0.001 is not 1/10, it's not 1/100th, it's 1/1000th. So we have negative 5 divided by 1/1000th. And if you divide by 1/1000th, that's the same as multiplying by 1,000, which is negative 5,000, which is pretty negative. And I think we can see that if we pick the number even closer to 1, like 0.999999, where the difference between that number and 1 is 1/1,000,000th, and then you flip the multiply, you end up with negative 5 million. So what's happening here is when we divide by a very, very, very small number that's close to 0, we end up getting a very, very large result. And I'm going to say this a lot. When we divide by a small number, we get a big result. When we divide by a big number, we get a small result. That's always the case because dividing by essentially is inverting the magnitude of the thing you're dealing with. So here, a positive number divided by a very, very, very small negative number is going to get really, really, really negatively large. Okay, so here's some language slash notation slash, there's another word I'm looking for here. Definition? I don't know. There's a word I'm looking for I can't think of. Nomenclature? No, that's not it. Anyway, this limit is negative infinity. And this limit also doesn't exist. Those two things are both true. So when we say a limit's negative infinity, well, when we talk about a limit existing, that means the function is getting really, really, really close to some particular value. That's not what we're saying here. The function isn't getting closer and closer and closer to the number negative infinity. It's not a number. It's just an idea. It's a direction. It's saying, oh, as x gets close to this one particular value, 1 in this case, the function just gets more and more and more negative. It decreases without that. Graphically, it's like having a vertical, it's not like, it is having a vertical asymptote. So this function, 2x plus 3 divided by x minus 1, would have a vertical asymptote at x equal to 1. And at least from the left-hand side of 1, it's going to get super duper negative. Like that. So it is correct to say the limit does not exist. But it's more correct to say, yes, I know the limit does not exist, and also the function is getting super duper negative. This says all of that. So the most correct thing to say here is that the limit as x approaches 1 from the left of 2x plus 3 over x minus 1 is negative infinity. On the other side of things, the limit as x approaches 1 from the right-hand side of 2x plus 3 over x minus 1. So now if I think about it, well, the numerator is still getting closer and closer to 5, and the denominator is still getting closer and closer to 0, but now the denominator is very, very slightly positive because we have a number a little bit bigger than 1 minus 1. And a positive number divided by a positive number is a positive number. So this is going to get very, very positively large.
The sign of infinity is always going to be the sign we're approaching from.
Say that one more time.
The sign of infinity is always going to be the sign of the side we're approaching.
Definitely not. It happens to be in this case, but it's based really on the combination of the sign of the numerator and the sign of the denominator. So, and I'll point out real easily, if my function were instead something like the limit, or if my limit was something like the limit as x approaches 1 from the left of, say, 2x minus 7 instead of 2x plus 3 over still x minus 1. Now, if I plug in 1 to the top, I get 2 minus 7, which is negative 5. The denominator, since I'm coming at 1 from the less than 1 side, the number less than 1 minus 1 is slightly negative. And then a negative divided by a negative is positive. So it's not the side so much as what the overall combination of signs are doing. And then we can see that from the other side, limit as x approaches 1 from the right of 2x minus 7 over x minus 1 would in fact be negative 5 over a slightly positive number, which would be negative infinity. So it's all based on the sign. So typically, when you have a limit that's a non-zero number divided by 0, your job is just to figure out whether the whole thing's positive or negative, and then say the answer is either positive or negative infinity. That said, I should have written this over here. Here we could also ask about the two-sided limit. Well, you could always ask about the two-sided limit. And we would say, in this case, the limit as x approaches 1 of 2x plus 3 divided by x minus 1. Well, the left side is negative infinity. The right side is positive infinity. And since those are doing totally opposite things, the overall two-sided limit can't be equal to just one of them. So the two-sided limit does not exist. It really actually doesn't make a whole lot of sense to talk about the two-sided limit here, but sometimes people do, so we should. Let's look at some more examples. So let's look at, we should actually be, yeah, how general do I want to be here? What time is it? We still have half an hour? Okay. Yeah, let's do this as well. So we're kind of in the land of infinity right now. Talking about things that either have a limit that ends up being infinity or taking the limit as x goes to infinity. So let's look at actually this one again, but now we're actually going to look at the limit as x goes to infinity of 2x plus 3 divided by x minus 1. And there's a number of ways to do this, but we could just start plugging in numbers, right? If I, let's say, you know what, instead of trying to actually write numbers, let's just kind of use the tools we have. So if we have 2x plus 3 divided by x minus 1, actually I want to do something, I'm going to zoom way in here. Yeah, cool. In parentheses. Cool, I can zoom out a little bit, I guess. Sure, you can't even see the right-hand side. There we go, cool. So, what we could do here is use the table and start plugging in larger values of x, like say 10, or 100, or 1,000, or a bajillion. I mean, that's not really a bajillion, it's a million. Hey, it looks like we're getting really, really close to 2. And we are. This function, as x gets really, really large, gets very close to 2, because what we really have here is, right, say, if x is equal to 1,000,000, then we're going to get 2,000,003 divided by 999,999, which is essentially the top being, twice the bottom. It's pretty much 2. Now, how do we deal with a limit like this? Well, there's a shortcut, but you don't really get to, it's kind of like L'Hopital's rule. You can't use L'Hopital's rule until you've learned how to do it the longer way first. There's a shortcut for this that we're not going to learn until we do it the long way first. And the long way is really to divide everything by the highest power of x that is in the denominator. So in this case, the highest power of x is x to the first. So I'm going to rewrite this as the limit as x goes to infinity, and divide every term in the numerator and the denominator by x to the first. 2x divided by x, 3 divided by x divided by x, 1 divided by x. Simplify. So the limit as x goes to infinity of 2 plus 3 divided by x over 1 minus 1 divided by x. And now, we're going to remind ourselves that if x is getting really, really big, something divided by x is getting really, really close to 0. So that means that 3 divided by x is going to get really small. And 1 divided by x is going to get really small. When we evaluate this limit, we end up getting 2 plus 0 divided by 1 minus 0, which is 2. Yes? I didn't divide by 0. So what this notation here is telling me is that this thing I've circled is getting closer and closer to 0. That's what I'm writing with. I'm assuming you mean what I'm doing right here. Right here. So I'm not dividing by 0. I'm dividing everything by x. So the rationale for doing that is so that I can kind of see what's happening. So I know that x to the first is kind of the dominating term in both the numerator and the denominator. So it's going to help me see kind of what's left over, what matters. Let's look at another example, and I think it might become a little bit clearer. So let's say we have the following example. Yeah. We'll look at this function, f of x equal to, sure, x squared plus 3 over x plus 1 squared. And we're going to look at the few, sure, that's fine. So let's first look at what's happening as x approaches -1 from either side. So if we look at the limit as x approaches -1 from the right-hand side, okay, so I'm trying just to plug in -1. So on the top, I get -1 squared, which is 1, plus 3, which is 4. And the denominator, -1 plus 1 is 0, but I'm going to ask myself, is it a slightly positive or slightly negative number? And it's always a little tricky when the number is negative. So I think a number line helps. So if I'm a little bit to the right of -1, I'm over here like at -0.99. Right, that's a number that's a little bit bigger than -1. So -0.99 plus 1 is slightly positive. Although it doesn't actually really end up mattering here because your slightly positive number squared will definitely be positive. So here we have a positive divided by a positive, which is going to be positive infinity. On the other side of -1, the limit as x approaches -1 from the left-hand side of x squared plus 3 over x plus 1 squared. Still going to get 4 on top when I plug in -1. But in the denominator, a number a little bit less than -1, like -1.01, right? It's more negative, so it's less, which I know is kind of terrible, but that's the way the negative numbers work. So -1.01 plus 1 is still just a little bit negative, right? It's -0.01. So it's a negative number, but then it's going to get squared, which means it's going to be positive. So we probably didn't even have to actually think about it a whole lot because we knew that no matter what, the denominator was going to be positive. So here you have a positive divided by a positive, which is going to give us a positive infinity. Sorry, I can't see that. And if you wanted to, you could, in fact, say that the two-sided limit, the limit as x approaches -1 in general of x squared plus 3 over x plus 1 squared is positive infinity. Because the left-hand side and the right-hand side are both going in the same direction. I will again point out, this still means the limit doesn't exist. We're just being more specific about which way it doesn't exist. Yeah, I told you the limit doesn't exist, and also the function gets really, really big. That's what I'm saying by writing this symbol here. Okay. Back to the question that spurred this example. What about the limit as x approaches infinity of x squared plus 3 divided by, I'm going to multiply at the bottom and write it as x squared plus 2x plus 1. So the idea here really is that as x gets really, really big, these terms with lesser powers don't matter that much. Like if x was a million squared is a trillion. A trillion plus 3, okay. And the bottom, a million squared is a trillion again. A trillion plus a 2 million, that 2 million, although it's a big number, not compared to a trillion, it isn't. That trillion is the only thing that really matters in the bottom. So as far as we're concerned, if we plug in a million, the only numbers that really matter are the trillion on top and the trillion on the bottom. And the rest is just trash. So that's why we're dividing the top and bottom by the thing that's the biggest or to the highest power. The thing that I would say is growing the fastest. It is the dominating term and it's the most important thing. So we're going to divide everything by that to help us see what the limit's going to end up being. So we divide everything by x squared. Some people prefer to factor out an x squared. That also is totally fine. In fact, I'll do it that way next time. So I'm going to still divide everything by x squared here. In the next example, I'll factor out the highest power instead, just to show you how it looks a little different. So we divide everything by x squared. You can totally skip this step of actually writing it out and actually simplify each term, because that's what I'm going to do next. So I divided everything by x squared, and then I'm going to rewrite it so that each term is simplified. So x squared divided by x squared is 1. 3 divided by x squared doesn't simplify. X squared divided by x squared is 1. 2x divided by x squared simplifies as 2 divided by x. And 1 over x squared is 1 over x squared. And then anything that's getting divided by x or a power of x, since x is getting really, really large, 1 divided by x squared is getting really, really. So all the things that are being divided by x squared or divided by x, whether it's 1 or 3, right? 3 divided by a bajillion is still very small. It's like if you had $1 and tried to spread it out among a million people, or $3 and tried to spread it out among a million people. Everyone's still getting fractions of a penny. Close to 0. Close to 0. Close to 0. So we're left with 1 plus 0 over 1 plus 0 plus 0, which is 1 over 1, which is 1. And what this really says is that as x gets really, really large, the function gets closer and closer to 1. Or in other words, this function graphically has a horizontal asymptote of y equal to 1. So graphically, here's what this looks like. Again, this is not a perfect graph. This is just to kind of show you what's going on here. If I was going to graph f of x equal to x squared plus 3 over x plus 1 squared, we would have a vertical asymptote at -1. We'd have a horizontal asymptote at +1. I will also point out, because it's worthwhile, we'd have a y-intercept of -3. -3? Nope, +3 by plugging in 0, right? If x equals 0, f of 0 is 0 plus 3 over 0 plus 1 squared, which is 3. And then we know that as we approach 1 from the, as we approach -1 from the right-hand side, we go up to infinity. And then we go this way, we get closer and closer and closer to that. And on the other side, same sort of deal. All right, I'm checking something real quick here. Technically, I've drawn this slightly wrong. Technically, this graph should actually do this. And cross its horizontal asymptote. It's not something you need to worry about right now, but the reason I actually care is because I just want to make sure that you all know. So I shouldn't have graphed it like this. Sorry, I know it's terrible. I want you to be aware that it is possible for a graph to cross its horizontal asymptote. It is not a hard barrier that can't be crossed. All horizontal asymptote is it says that if you go way out that way or way out that way, the function gets closer and closer to that value. It says nothing about what's going on in the middle region. So totally can cross the horizontal asymptote, happens all the time. On the other hand, you cannot cross a vertical asymptote unless someone is really, really trying hard to make it happen. You can, it's weird though. It definitely has to be a piecewise function, and you should never worry about that. It's not going to happen. Okay, let's see. What else have we got here? Oh, we should talk about that. Let's do one more example like this though. So let's say I had something like, sure, f of x equal to, sure, let's say 3x divided by x squared minus 4. And I want to talk about, really, I'm trying to talk about the asymptotes here. So, oops, sorry. There's probably an asymptote, a vertical asymptote. I'm going to look at just one of them, although there are two of them here. The vertical asymptotes at both x equal to 2 and x equal to -2. Let's specifically hone in on 2 for a second here. And let's see what happens as we approach 2 from either side. So we look at the limit as x approaches 2 from the right-hand side. Okay. We plug in 2, we get 6 over 0. Slightly positive or slightly negative? Yeah, slightly positive. Sometimes it can be hard to tell. If it's hard to tell, it usually means we want to do some factoring. In fact, we could have factored this out here and written this as 3x over x minus 2 times x plus 2. And then it's a little easier to see that, oh yeah, the x minus 2 part is going to be slightly positive, and the x plus 2 part is going to be close to 4. So it's still positive. So this is going to be positive infinity. On the other side, the limit as x approaches positive 2 from the left, well, the top is still getting close to 6. And now we have a number a little bit smaller than 2. If you square it, it's a little bit smaller than 4. Subtract 4, it's a little bit negative. So here we're getting negative infinity. What about a horizontal asymptote? So in this case, I want to divide the top and, well, I was going to factor out this time instead of divide. I want to, instead of divide the top and bottom by x squared, I'm going to factor out an x squared from the top to the bottom. It essentially achieves the same results. Some people just like it better. Some people, the limit as x goes to infinity of 3x over x squared minus 4. That's going to be the limit as x goes to infinity of x squared times, let's see, if I factor or divide out an x squared, I'm left with a 3 over x. In the denominator, if I factor or divide out an x squared, I'm left with, well, x squared divided by x squared is 1, and 4 divided by x squared is 4 divided by x squared. I personally prefer just to divide each thing by x squared because it gets to the same place, but some people like doing it this way. And then the x squared divided by x squared is just 1. So we end up rewriting this as the limit as x goes to infinity of 3 over x over 1 minus 4 over x squared. And then as x goes to infinity, 3 over x gets really, really small. And 4 over x squared gets really, really small. So we have 0 divided by 1, which is 0. And this is generally true in that if your degree on top is smaller than your degree on the bottom, that means the denominator is growing much more quickly than the numerator. And so your fraction is going to have a denominator that's much larger, and it's going to get smaller and smaller and smaller. For example, right, if I plugged in 1,000,000, you'd have 3 million divided by 1,000,000,000,000. Oh yeah, 3 million divided by 1,000,000,000,000 is very, very small. So I'm trying to think about if I should start talking about this next thing or not. No one's teachers have started talking about delta epsilon proofs yet. Okay, but I think it's coming up because I saw it on one of your homework assignments already. Yeah. We should start doing that. Okay. No, we should not. We'll save it till Tuesday. It's a lot to introduce in the last 10 minutes of class, and I would be doing you a disservice if I started trying to talk about it now. I'd be like, okay, we're done. So we'll save that till Tuesday. We'll do a few more examples of limits here. Let's look at a couple more things. So let's talk about this function. X squared divided by x minus 3. So we've seen some rational functions now where the degree on top and the degree on the bottom are the same. The previous example, the degree on top was less. And this example, the degree on top is greater. And we're going to look at both, again, the asymptotes here. So vertical asymptote, it's going to be x equal to 3. And we're going to see from the right-hand side, well, let's take a look. Limit as x approaches 3 from the right-hand side. We're going to get 9 over a very slightly positive number. It's going to be positive infinity. I will say, if you're asked to do a one-sided limit like this is like all the work you should show. There really isn't any other work to be done here. other than, great, I got not 0 over 0. The overall sign is positive. Boom, I'm done. It's positive infinity. Like, there's nothing else to say here. On the other side of 3, or I should say, as we approach 3 from the other side, we get 9 divided by a slightly negative number, so negative infinity. I'm not gonna write horizontal asymptote because there isn't one, but I'm gonna write, if we look at the limit, as x goes to infinity of x squared over x minus 3. Now here's where it's really easy to make a mistake. Or not a mistake, to make life harder on yourself than it needs to be. We're gonna divide, I like dividing better, the top and bottom by x to the first power. Because you want to divide by the highest power of x that is in the denominator. Here's why we don't want to use the highest power in general. If I were, so again, I would say don't write this down. If I divide everything by x squared, look what happens. I get the limit as x goes to infinity of 1 over x. Sorry, 1, not 1 over x, apologize. On the bottom, it's 1 over x minus 3 over x squared. Okay, great. So if I plug in infinity, I get 1 over 0 minus 0. Was that denominator slightly positive or slightly negative? I don't know. It's really hard to tell. That's why I don't want to do it this way. Because it really, really makes it much more challenging to see if the overall sign is positive or negative. Instead, we're going to do the easier thing. We're going to divide everything by x, not x squared. If we do that, look what happens. X squared divided by x is x. X divided by x is 1. 3 divided by x is 3 divided by x. Now, the denominator is going to be 1 minus 0. And what's the numerator? I spit water all over my face. A very big number, which we call. So infinity divided by 1 minus 0 is infinity. So what that means here is that as x goes way, way to the right, the function just gets larger and larger and larger. And similarly, if we take the limit as x goes to negative infinity of x squared over x minus 3, which would be the limit as x goes to negative infinity of x over 1 minus 3 over x, we would get negative infinity over 1 minus 0, which is just negative infinity. So way to the right, the function gets big. Way to the left, the function gets negatively big. In the middle, some stuff happens. This is an example of a function that has what's called not a horizontal asymptote, but a slant asymptote, also called an oblique. Most of the time, no one's going to ask you to find a slant asymptote. You only get a slant asymptote if your degree on top is exactly 1 larger than the degree on the bottom. If you wanted to find it, here's how you'd find it. You would do the polynomial division. So if you do this division, x squared divided by x minus 3, say x times x gives you x squared, x times x is x squared, x times minus 3 is minus 3x, subtract, x squared minus x squared is 0, minus 3x is plus 3x, and then you say x times what gives you 3x? Oh, it's plus 3, and actually you can stop right there. If you wanted to, you could finish it off and say 3 times x is 3x, 3 times minus 3 is minus 9, subtract 0 plus 9. So what we're really saying here is that this fraction, x squared over x minus 3, can be rewritten as the quotient plus the remainder divided by the divisor. All right, this is what you get when you do the division. And then there's still a 9 left over that has to get divided by x minus 3 that you can't do anything with. And so as x goes to infinity, this part here gets real small. So the graph essentially kind of looks like y equals x plus 3 plus a little tiny bit that gets smaller and smaller as you move further away from the origin. So here's how this graph looks. Now, this is most of these are a little less steep. I will point out it's not me. This is too steep. So if I'm in the graph of this function, f of x equal to x squared over x minus 3. Vertical asymptote of 3. If I have a intercept at the origin, right, if x is 0, I get y equal to 0. And my slant asymptote is y equal to x plus 3. So it's like I'm drawing the line x plus 3, which has a y-intercept of 3 and an x-intercept of negative 3 as an asymptote. And then I'm going to look at my useful limits over here. I know that as I approach 3 from the right, the function gets very, very positive. So as I approach 3 from the right, I'm going to go up this way. As I approach 3 from the left, it gets very, very negative. Then I'm going to go like this. I'm going to hit that intercept right there. And then I'm going to get closer and closer and closer to my slant asymptote. I'm going to get closer and closer and closer to my slant asymptote. That's how that function looks. And if you zoom way out, it kind of just looks like the function y equals x plus 3. In fact, why am I trying to draw these graphs when you could see a much nicer version of them? Let's check it out. So if we graph y equal to x squared divided by x minus 3, right? Yeah. Zoom out. Let's look at the normal. And then if you graph the slant asymptote, y equal to x plus 3, oh, look, they essentially look pretty much the same if you move away from the middle. In the middle, they're very not the same. But the further this way we go, the closer and closer and closer they get to each other. They never actually touch each other, but they do get closer and closer to each other, just like any asymptote a function gets closer and closer to. Yeah. So what else to say here? I know I only have a couple minutes left. I just want to make sure I'm not leaving anything vital out. Oh, that's fine. So here's what's coming up in your future. I certainly have seen this on, I don't remember whose homework assignment it was, or it was actually this worksheet from, I don't remember whose class this was. I definitely saw some delta epsilon stuff. Yes, right there. So here's a preview of what's coming up. Delta epsilon proofs, also known as the precise definition of a limit. So essentially what we're going to be asked to do is to prove that the limit's what is equal to. Often the limits are really easy. Like, for example, the limit as x approaches 3 of 2x plus 1. We know that limit's equal to what? 7. But our job is going to be to show it in more detail. And what that really means, and I'm just going to say the words here, is that we're going to show, I'll write down the words here. We're going to have to show that the function f of x equal to 2x plus 1 can get as close to 7 as we want. How close? Within 1? Within a half? Within a tenth? A millionth? A billionth? A trillionth? How close? However close we want, which is usually what we're going to call epsilon. So the idea is we're going to think of epsilon as being some very, very small number. And we're going to say that we can always get to within epsilon of that limit. And the way we're going to get there is by letting x get as close to 3 as needed. And I'm going to say one last thing. In this example, I will say, but I won't show, but I'll say, we can get the function 2x plus 1 to within 1/100th of 7 by making sure, or by letting is the word I should actually use here. Letting X get to within. Sorry, I have to remember which way it goes here. Oh my gosh, my brain. Sorry. Double it. Yeah. 1/200th of 3. And I know this might seem like where am I coming up with these numbers from? Cliffhanger. We'll talk about it next time. We'll talk about it next time because we're out of time. Or in office hours, you come to office hours. But that's kind of the general gist, is that you have to let X get really, really close to whatever X is approaching so that you can say that the function is close enough to what the limit value is. And that then proves that as X approaches blank, the function approaches the limit value.